Recording is in progress. Good evening, y'all. This is Go Platoon, evenings and weekends. This is Golf Platoon. I'm your host, Jordan. Today, week 6. It's week 6, y'all. Look at that. By week 7, we'll be doing web stuff. This is fundamentals, and by God, this is a fundamental thing. We're going to talk about it and learn about it, and hopefully commit it to memory and look over it before you walk into a coding interview. That's one of these things. I don't expect you all to be big O experts after this. I expect you all to be better at it than I am at it by the end of today. That's a very low bar, and you're going to be there if you finish these assignments. That's about where I want you for walking into interviews. Big O notation. I think this PowerPoint does a good job of covering most of this. We're going to look at it shortly. But how do programmers communicate and think about program efficiency? We use Big O. It is just a measure of time that it takes to perform a function based off the number of inputs. If you got inefficient code, it's going to go slower, and we're going to have an equation for how much longer that takes, right? This comes up in coding interviews often. You should be able to explain when your code is efficient or not. And really, what I truly want you to be just thinking about, your big takeaway from this is if you're doing something and your big O notation for this thing is like, this, maybe not that, sorry, this quadratic, maybe we think about more efficient ways to get that done. In a lot of cases, speed is only as important as how quick you need it, or the number of things you're doing, right? We don't need to run through a list of 15 things as efficiently as possible. Who cares? If we're triple for looping, through 3 arrays, each of them are 10 things long, 10, I guess, a length of 10, whatever. It's not that big a deal. But when we start getting around like 100,000 and we're doing things hundreds upon thousands of millions of times, maybe we shouldn't be doing that, right? That's the takeaway. But here's big O notation, as told by PowerPoint. Starting at, wow, that's so bright. Big O. Is it me making it this bright? Yeah. All right. Understanding algorithmic efficiency, or at least understanding what we're talking about. Some of y'all may go on to do bigger and better things where big O is all you think about. So we'll see. We're not all going to end up there. We got some resources here. I don't want to, look at these while, as a group and film that. There's a visualization of how long some of these methods, I guess, sorting methods and whatnot, can run through things. Here's some documentation for benchmarking some of those searches. That's where these kind of conversations end up ultimately. But what is big O? It's just a complexity of your function. The O is complexity of the function in terms of the input size, which is going to be n. This is almost all you need. O of 1. Speed does not depend on the size of the data set. We're going to look at an example of this on the README, but that's basically if I had a function that said equals blue, and all it does is return true or false if the string inputted to it is blue. That is always going to complete at exactly the same speed. It doesn't matter. It only ever accepts one thing, right? 10x, but 2 times more time. Let's skip that for just a second. I want to talk about O of n. This is 10 times the data, means 10 times more time. That is if you had a list and you were going to iterate through it one time. You're going to run a for loop on a list. If there is 10 times as much data, it's going to take you 10 times as long to get through that. That's fine. That's not that big a deal. If that needs to be faster, if the data is so large that just iterating front to back is not acceptable, that's where we're going to start getting into our sorting algorithms, our search algorithms, stuff like that, where 10x the data means 2 times more time. Something like a binary search is going to be a lot closer to this than it is to this. right? Because it's not searching all the data, it's halving it and then halving it and halving it. O in log n, 10 times the data means about 20 times more time. I'm gonna see. We got an example of that. O in 2. This is another very common one. Do y'all know what O n squared is? Can y'all guess? This is a loop.
Is it
What is this? Say again?
is it nested loops?
Absolutely. And you want to know how you can tell how many, how many nests deep we are? This exponent right here. If we were triple for looping, this would be n to the third. What is that? Third cubed, n cubed. And then there's this. I don't know. Is this Star Trek? Do y'all know what are these? It's not Star Wars, right? The lithium crystals. It sounds like nerd shit. Star Trek probably. Star Wars is all about the fights. Star Trek's about diplomacy and whatever. Actual sci-fi, whatever. There ain't no dilithium crystals in Warhammer, all right? We got warp drives. As we talked about, O1, constant time, is actually a good example of this as well. Like I said, first element is red. You take an array, but this is a good example, right? This array could be as massive as you want it to be. It doesn't matter. We're always going to complete immediately because all this function is doing is checking the very first element, seeing if it's red. This is not a great, it's really hard to always be O of 1, right? You can't just expect that. But just so you know, the most efficient program is one that doesn't care if the size of the inputs, is larger, right? That's kind of what we're talking about here. We're just checking the first one. If it's red, great. If it's not, kick it back. Done. We're not going to iterate. I didn't look up what this means. Pigeon race versus internet speeds. What else is talking about? Oh, okay. Well, okay. This is what we're talking about, right? A pigeon race versus internet speeds, a pigeon versus internet speeds race. The pigeon is always going to done exactly the same amount of time, right? No matter what. The pigeon is delivering a CD. It doesn't matter if that CD or let's say USB, makes more sense. If that USB has, 7,000 videos on it, or one video on it, that pigeon is still going to deliver that USB, that information to the place it needs to get to, regardless of that. Whereas if you're trying to upload videos via the internet to go somewhere else, more data takes longer, right? There's potential that a pigeon could beat the internet if it's a short enough race and enough data, right? Just a thing to think about, I guess. Linear time, runtime will grow linearly based on what you pass in. Like I said, for loop doesn't contain array values for item in array. If item equals value, return true, return false. This could complete immediately. If it's the first thing, it could, run until the end. Doesn't matter. The more data you give this for loop, the longer it's going to get, to run. More money, more problems. Sure. Does that make sense to anybody? If you need more examples, we can dig in, but these are the big ones. Quadratic time is the other one I want you to think about, and why, if you're ever, nesting a loop in a loop, I want you to think very, I want you to really talk about it and explain why you want to do that. 9 times out of 10, and by that I mean pretty much 10 times out of 10, you're just trying to like bulldog your way through it, right? There's probably an easier way to get what you need without having to iterate through every single, array element, and then for each of that, run through another array, things like that. There's usually an easier way. There's times where this is just what you're going to be doing. But think about those times, and these are fine. You're a nested for loop. No one's going to come beat your door down and say, "How dare you!" Like, make it work and then make it right. If this gets you there, great, and then make it right. If this gets you there, great, but then start thinking about how you would refactor it. Or we're talking about interviews. You can write a for loop in an interview and nest it, but at the end of that interview, you should say, I did not, I wouldn't leave this way. I just wanted to get that information to see if I could work it. I'm probably going to go back and filter before I get to the for loop because I already know I don't need all of those. Or I'm going to find some other way to not have to, blast through all this at one time. Maybe I'll match some of these things first and then just run through one array. Just something to make it not this. Because even, and like, people, say like, oh, well, double for loop, that's just a simple way to get it done. It's like, well, not really. Double for looping starts getting complicated to explain. There's usually, if not faster way, a more straightforward way than kind of looping and then doing something for doing something each time to do something. It's easier to explain. I filtered out all of these and then I ran through them, right? And it's going to take double the amount of time, right? As your input gets longer. Key takeaways as we give you something we haven't explained yet. Searches through hashes are faster than searches through arrays because hashes don't keep track of indices. What the heck's a hash, Jordan? You've never used that word before. Any guesses?
Not like a dictionary where you have a key that goes straight to that position.
Yep, that is what it is. A hash. There are a lot of languages that use the word hash. The first one that comes to my head is Ruby, but I'm pretty sure there's hashes in Java. In fact, I'm certain there's hashes in Java. It's constant lookup times, right? We don't have to iterate through a dictionary if we know what the key is. Think about those kind of things. Build out, we're talking Python, we're talking JavaScript, build out a dictionary, build out an object. If you need to reference data that you've, stood up, it's going to be faster. Again, if speed's not important, what does it matter? But just, it's a good habit to build good habits, I guess. If you got to reference information that you've gathered, think about maybe putting it in a dictionary. Wherever possible, avoid nested loops. Like I said, avoid it when possible. If you find yourself writing code that has poor big O complexity, consider refactoring. These are great takeaways. Number 3 is truly what I want y'all to leave this lecture with in your head is I'm writing really crappy slow code. Let's at least consider refactoring. Maybe you put a note that you want to refactor it. Just get in the habit of identifying inefficiency in your code, making note of it, fixing it at the end, or at least be able to explain why you should fix it, why you'd want to fix it, right? That PowerPoint is pretty much all I want to talk about for most of this. We can run through constant time, but I don't think we need to beat that one on the, we don't need to beat that horse, right? You run through one time, not for each in the array, you're O of 1. Does that make sense? Anyone have questions about O of 1? It's okay to, because these are all new terms, and even if I'm making it seem simple, it's new terms. So if you need to talk about it more, we can.
So
Is
the
the idea to just be able to like look at our code or think our code out and see like, well, I guess what looks like it's more efficient?
The idea, and we'll get to those in the challenges for today, you should be able to look at something you have written and say, this is log O, this is O of 1. This is this is n squared. You should be able to talk about the efficiency of the code you just wrote. And that's what we'll be doing in the assignments. And that is kind of what I want you to be able to identify, basically. You don't need to know all of them. We don't need to get deep down to every single type of, big O notation that is common, but basically you should know constant lookup, you should know loops and nested loops. And then maybe, binary search, things that we got an example of that here, log in. Mike, did that answer your question, or did you have another one?
Well, I guess when I was looking at what it was saying for O of 1, so it would seem that it's like the basic instructions that are just simple, whether it's
Well-
true, false, if it's going to get the data from the index of an array or the key from the hash, if it's evaluating greater or less than, that's what it seems like. Just very
Yeah, basically any code that returns a Boolean, or just a single, thing, that a single element, that is O of 1, right? These return true or false. If returns true or false, else returns true or false, right? If it can be solved with a quick run through of here, is it true, is it false? Done. O of 1. Doesn't matter, like we said with the other array, or the other example, you can take a massive list, but that function just looks at the first one in that list, basically just opens it up, says, oh yeah, this is true or false, yay or nay, whatever. Who cares? Who cares if that list is a million, elements long? You're only looking at the first one. So the time to run it is not going to matter. It's not going to change if the input is larger.
Thank you.
Is that okay? Yep. Linear time, O of n. This is linear time. For most algorithms, the amount of work performed is dependent on the inputs. With linear time algorithms, number of inputs and the amount of work completed have linear relationship. In other words, as the number of inputs increase or decrease, so will the work. Yada, yada, yada. If you want to run a for loop, it's going to increase linearly. Does that make sense? If I have to iterate through a list and the list is longer, it's going to take longer to run it. 10 times the data, 10 times the runtime. That one should be the easiest to understand, so you should remember it. O event, that's a for loop. That's a big one. Be able to just spit that off. Here's an example of a for loop. Quadratic time. An algorithm is said to run in quadratic time when the amount of work done is proportional to the square of the input size. So the size of the input increases, the amount of work increases at a much faster rate. Double for loop, right? Array is this, array length of array, whatever. We're running through a range for the length of the array. And then again, for the same length of the array, we're doing all of this. Every time this gains or goes up by 1, we're basically squaring the amount of, not squaring, the square of the input size. It's going to get larger, 100 times longer for 10 times the input. That makes sense. Nested twice, then that is nested to the power of 2. 3 nests, nested to the power of 3. Make sense? Log time, log in. This is logarithmic time. I haven't done algebra in a while, not since nuke school, and that was dummy math. So I kind of forget what some of these terms mean. But log time, logarithmic time, versus logarithmic functions in mathematics. The logarithmic function tells us the number of times that you have to divide the number by a base. The base is 2 in our case, to get 1 or less. In terms of algorithms, when an algorithm's logarithmic time complexity is given in inputs, the algorithm would take log in steps to complete the job. What does that mean? We talked about it in the slide. Just refer back to that real quick. 10 times the data means 2 times the time. This is really efficient. Let's aim for this when we can, right? When it matters. If our list is 10 elements long, I don't want to do this. Maybe this is fine, but if we really need to worry about speed and complexity, this can be a big win. But it's all about the win, right? If your process runs in 0.5 seconds, with this. Do we want this or not? Are we returning information to a user who just wants to see pictures of cats? I think 0.5 seconds is plenty of time. I think that's great. Are we doing high frequency trading? And I want to know within a nanosecond if prices went up or down, if they look like they're going to go up, they look like they're going to go down. Absolutely, I want this. That's worth a lot of money. But it all depends on what you're doing. Does that make sense? Oh God, who's good at math here? Shoot, what was it? Was it Hamilton's we looked over who had the real nice code for the solution? I was hoping somebody could walk through this better than I can, but I'm gonna kind of talk about it at least at some level. Don't expect me to explain this to you in a way that makes sense beyond surface level. What's going on here? This function takes a base and an exponent, and it tells you basically if you raise the base to the power of the exponent, you should get the answer, right? 32 is 2 to the 5th. If you multiply 2 by 2 by 2 by 2 by 2, should return 32, right? This is logarithmic, or sorry, not logarithmic. This would be, if we were just going to solve it like I just did, just 2 times 2 times 2 times 2. If you just do it that way, that's going to get, it's going to be a linear growth depending on the exponent number here, right? You're always going to have to add 1 each time. That's pretty good. But what if you didn't? How could we make this faster? Well, if I didn't want to run through each and every one of these exponents each time, maybe I wouldn't have to. Maybe I take the half power times the base. Ultimately, this is what I want to do. I don't want to multiply 2 times 2 times 2 times 2 times 2. I want to multiply 2 times 2.5 times 2.5. Then that should be it, right? Am I wrong? I didn't check that math before I said it to y'all. 2, that's not going to work, right? Oops, times 2.5 times 2.5. That's not it. That's 12 and a half. But this is recursive, so it's going to run more than once. But look what we're doing. We're trying to determine the half power so that we don't have to run through the exponents each and every time. So we're going to take base in the exponent. If the exponent is 0, return 1. We're not going to hit that. If the exponent divided by 2 is equal to 0, or sorry, modulo 2 equal to 0, well, it's 5. It's going to have 1 remaining. So we'll go to the else. Setting half power is equal to base exponent minus 1 divided by 2, get through, flat. So at this point, we are going to recurse handing 2. The base is not going to change at all, but the exponent will. 5 minus 1 divided by 2 is 2. So we're going to run back through here with 2 and 2. Skip that. 2 modulo 2 will be equal to 0. So we're going to grab half power here. Base exponent divided by 2 should be 1. We're going to run through it here. Get there. That's going to return this the first time, this the first time. And then we're going to have these. I don't want to run through it all because I hate math. This is an example of O of N. If you really, we should have showed you something we've shown before, like your binary search. What's going on? Somebody, yeah, whatever. Doesn't matter. I can't explain it super well, so maybe that tells you how important it is that I think you learn it. O N log N. Oh God. Don't let the notation confuse you. N log N, simply the amount of work done grows in proportion to the product of input size. N multiplied by input size log N, or simply N times log N. Several sorting algorithms such as merge sort, heap sort, run an O N log N. Who cares? Look at logarithmic searches, right? And Google, what is their big O efficiency? Memorize those and you're good. We don't need to go through and calculate all of this stuff. We're not nerds. We're trying to do software development full stack, right? Anyways, other type of complexity cases, there's all kinds of others. We aren't going to get into every single one of them, but you should be able to explain a few of these. Cubic. How do we get cubic? Someone want to take a guess? We didn't even use this word.
3 nested loops.
That's right. Wait, what? This one here, what's this? Jonathan?
Quadratic, is it? Looks like the two nested, but it's not.
Yep. Yeah, I don't know if that's technically quadratic. Is it? Yeah, no. Yeah, this is one loop, or sorry, 2 loops nested. This one here, what's this? What do we got? Who do I want to call on? Megan. Linear. How do we get, oh no. How do we get linear big O notation?
Linear?
Mm-hmm. It goes up constantly. How do we get that?
Y equals mx plus b.
Well, yes, exactly. But what has a linear lookup time or a linear runtime in
Oh,
common?
just one for loop, right?
Yeah, absolutely.
Okay, sorry.
No, you're good. Constant. How do we do constant, Sean?
That's going to be like a Boolean value or just it gives it a direct output.
Dang straight. All right, lecture over. Oh, no, I'm just pausing the screen share.